What's up, guys? Today we're doing a question that my friend George asked me to do. This question is currently being asked by Amazon, Apple, and Google, and the question is called minimum path sum. Let's get to it. So to get right into it, the problem description is, given an m by n grid filled with non-negative numbers, find a path from top left to bottom right, which minimizes the sum of all numbers along its path. Note, you can only move either down or right at any point in time. So for the example with rows 1, 3, 1, 1, 5, 1, and 4, 2, 1, you take the path 1, 3, 1, 1, 1, and then you output 7 because that's the minimum sum path, and the sum of that path adds up to 7. So cool. The first things I think about when I read a question like this is that we need to keep track of three things: our state, our choices, and our base cases or termination conditions. So the state that we need to keep track of is our current path sum, our current row, and our current column. The choices we need to keep track of and then take at any point in time are given to us in the question, and that's that we can only move down or right. And then the base cases or termination conditions are that when we get to the edge, we are done and we can return that value. And then if we go too many rows down or too many columns to the right and we go out of bounds, we need to return because that's like an undoable path. So the first way I can think to code this up is just a recursive brute force. And what we can do here is I'm first going to keep track of the number of rows and the number of columns. And to do this recursively, I can just make a closure, which is a function inside a first class function. I'm just going to call this like recurse. And it's going to have a row and column value. And then at each level, we're going to want to make choices and then move towards our base cases. So to implement our base cases, the first one is if row equals n minus 1 and column equals m minus 1. So if we're at the edge, we can just return our grid. Or if row is greater than or equal to n, so we went too far, or column is greater than or equal to m, we can just return float infinity because we want the min sum path, and that's like a very large path, so we wouldn't want to take that. So now we can take our choices. And just this is base case 1 and base case 2, like we just discussed. And then now we can take our two choices. So choice down, this is our first choice, is that we're going to want to go one row down. So this is choice 1. And then choice right is our second choice, and that's that we'd want to go one column to the right. And this is choice 2. So now to pick the best choices, we just want to return our current grid. So the grid at row column plus the min of choice down, choice right. And then given that we have no syntax errors, we can just return our recursive algo, and this should hopefully work. Awesome, so it works. One thing you notice though, if you were to submit this, this would time out. And the reason for that is because you can see at each level, we're going to be making two calls back to the function we're in. So that's going to result in a time complexity of 2 because we're making two new function calls raised to the m plus n. So in a square grid, this would just be 2 raised to the n squared. But because we have m rows and n columns, we'll make these two function calls on the call stack m plus n times, and then we'll have a space complexity of O raised to the m plus n for the recursion depth and the space we take up on the call stack. So this is really not ideal, and what we'd want to do here is save the results to some of these like best paths and best subproblems, because really if you think about like that smallest like 2 by 2 grid, the best choice is like the best choices above you and to the left of you. So if you save the optimal subproblems, you don't need to recompute them. So the way we can do that, and I'm just going to make this approach 2 right below us, it's going to use everything we already did in approach 1. So this is going to be recursive with memo, and that's dynamic programming because we're storing our optimal subproblems. And all we're going to need to add here is just a memoization dictionary which is going to keep track of our rows and columns. And we're going to add this base case if row column is in memo. We just want to return that and not bother recomputing the subproblem. And I'm going to upgrade this to base case 1. And then after solving our subproblem, we just want to store this before we return anything. So memo at row column equals that, and return our memo array. And also, like, given that we have no errors in syntax, this should work and this will complete. So that's really awesome. And actually, this runtime will be MN, because we're going to be making more calls to the call stack. But because we're storing all these subproblems, we're not going to have the same problem we had in the past. And then our space is going to be MN as well, for the amount of space we'll keep in our memo array, or our memo dictionary. So I saw this timed out. It's because I didn't comment out our recursive brute force, but now you see this completes. So this is an awesome solution, but we can do even better by solving this iteratively. Quick aside before I go to the bottom-up solution, but I actually originally coded this up using Dijkstras, but Dijkstras actually ends up being slightly slower. It's E log V, which ends up being MN log MN, because E is the number of edges and V is the number of vertices. And MN log MN is slightly bigger than MN, which is the time complexity of approach 2, the top down, and approach 3, which we're about to talk to, the bottom up. I'm going to make a video coding this with Dijkstras because I think it's like a really good practice of using Dijkstras. But yeah, I just wanted to note that. All right, cool. Back to the bottom up solution. So we can improve this solution one more time by switching from the top down solution in approach 2 to the bottom up solution. So this is still going to have the same runtime and space, but it's going to be slightly more space efficient because we're going to be saving the calls to the call stack, because in that top down solution, we're making calls to our recursive function until we hit the base case. But in the bottom up solution, we're saving iteratively the solutions to our dynamic programming array and then solving it that way. So we save that additional space and because we don't have to use the call stack. So what we're going to need here is a dynamic programming array to keep track of the best paths. So we're going to set the we're going to be setting all the columns to 0 for each one of the rows. And then what we know here is that the optimal way to walk across the first row is to always go right, and the optimal way to walk down the first column is to always go down. So we can say we're just going to set these like that way. So we're going to say for column in range M, we're always going to want to be setting this part of the grid to 0 because we're going to be walking across, and we're going to be setting our dynamic programming array at 0 and that column to our current value. And then we're going to do the same thing for each row in range N. And we're going to say the current is equal to current plus the row at each column fixed. And we're going to set that row equal to the current value. So now what we need to do, since we have the optimal solution along the first row and along the first column, we can just say for I in range 1 to N and for J in range 1 to M. We know that the optimal solution that we're going to store in our DP array is equal to the current value in our grid plus the minimum of the row above us and the column to the left of us. So given that we have no syntax problems, this should hopefully do the job. So we're going to return DP at N minus 1 at M minus 1. And let's see, we don't have any syntax problems, and awesome. Cool. Thanks so much for watching, guys. Feel free to put any questions you have in the comments down below. I'm also going to be doing a Dijkstras rendition. Not that it's the best solution, just that I thought it was really interesting to solve this problem with Dijkstras. But cool. Thanks again for watching. Have a good one. Peace.